Okay, we're continuing on here, chapter 12 to wrap it up, hopefully. And last time we got into sort of temperature and dependence on the rate of the reaction. We saw the Arrhenius sort of plot where we do the natural log of A over 1 over the temperature in Kelvin. That again will give us a linear relationship with a negative sloping line, where the slope of that is equal to minus E of A over R. And again, graphically, as we talked about, you can basically solve for the activation energy. You could also solve for the frequency factor, which is A. Again, that proportion of molecules that have enough energy to get to the other side. And again, this is sort of a graphical type of version of the Arrhenius equation. You would obviously have to do maybe some conversions. I'm not natural log of A, I'm sorry. Natural log of K, there we go. Natural log of K on the y-axis there. And you have to take the K values that you have and convert them to natural log and take 1 over temperature, make sure it's in Kelvin and graph it. And again, you can graphically do that. There's also sort of the 2-point version of that equation where, technically speaking, if you kind of know 2 points along that line, you could just kind of mathematically go after it there. Natural log of K2 over K1 equals E of A over R, 1 over T1 minus 1 over T2. Again, Kelvin for our temperatures. R is our gas constant, 8.314 joules per Kelvin per mole. As we talked about last time, again, you definitely want to be careful using both of those values, as activation energy is usually given in kilojoules and obviously R is in joules. So you want to make sure you're not off by a factor of 1,000 there. You do have to do some type of conversion either to joules or to kilojoules, whichever way you want to go with it. We then sort of finished up talking about reaction mechanisms, and reaction mechanisms are basically the idea, again, that not all reactions, for example, occur in sort of a one-step process. They may be the result of multiple individual steps along the way that you could add up. And a reaction mechanism is sort of a proposed way at which you could get to an overall reaction. And those are usually made up of what are referred to as elementary steps, our reactions. And one of the places where we look for to make sure, for example, if we're given a reaction mechanism, maybe multiple steps and individual reactions, we do want to make sure a couple things for sort of a mechanism to be good or be plausible, I guess is another way of saying that, is obviously if you take all those equations and you add them up, you should get the overall reaction. So if you do get the overall reaction, that's good for that proposed mechanism. Obviously, if you run through it, thank you. If you run through it, and they do not add up to the overall reaction, then it's probably not the greatest mechanism there and not a good mechanism. Along the way, we obviously cancel anything that are like on opposite sides of arrows, right? That are the same, or you can reduce down. We also have what are known as intermediates in reaction mechanisms. And remember that an intermediate is not just, for example, something that you may sort of reduce down, but it should not be present in the overall reaction. So it is something that's made early on in the reaction mechanism, but by the time you get to the overall reaction and the ending reaction, it's gone. So it gets used up. So kind of made early, then used up in a later step. And that's what an intermediate is. So again, if you add up those steps, it's all good. You will be in good shape. The other thing that you need to make sure of for it to be sort of a good mechanism is the rate determining step, or the RDS, which is the slow step in the mechanism. And the slow step in the mechanism should always have a rate law that matches the one found experimentally. So if you go through and you determine that the rate determining step is or does have the same rate law as the one found experimentally, then it also is a good mechanism. So those are kind of the two things in a mechanism problem where you're given the mechanism. Those are two things you have to make sure adds up to the overall reaction. Rate determining step has a rate law that's equal to the one that's found experimentally. This is the only place really in kinetics where we actually do use the coefficients in those elementary steps as the orders. And because it's a mechanism and an elementary step in a problem, you can write a rate law for each elementary step using that. So again, we had something I think like 2a goes to b or something like that. So if you had this as an elementary step, you could write the rate is equal to k a, and then we would use the 2 here as the order. And again, that's the only place where it connects where you can kind of do that is when you're dealing with mechanisms. Any questions on that there? All right, then let's continue on. So we did one mechanism problem earlier here. And again, this is one type of mechanism problem where they just really want you to sort of explain, what's happening in this mechanism, what's maybe the slow step, the fast step, and stuff like that. So sometimes another type of mechanism problem is like the one we're going to look at here. In this mechanism problem, they want you to kind of prove, if you will, that this is sort of a good mechanism or a bad mechanism. So you have to kind of use the proposed mechanism to show some work and do some calculations, not really calculations, but some algebra and stuff like that to decide whether or not this is an acceptable mechanism for this reaction. So here's the overall reaction we're kind of shooting for here. And this is the proposed mechanism up here. And this is the observed or experimental rate law. So we want to kind of use uh, the mechanism above to show if this is a good or bad mechanism. So the first thing we want to do, obviously, here is add everything together, right? So to make sure that we do get the overall reaction. So if we do that, let's see what we got going on here. If we put a plus, we got something that's got to cancel, right? So the N2O2 looks like it cancels. My N2O as well there cancels. And I think that might be it there. Yep. So that's everything that will cancel. And what we will see if we keep everything on the left-hand side there, 2NO plus we have 1 and 2 H2s. Go to 1 and 2 waters there. And an N2, right? So the first part of making sure, yeah. Yeah, so when you add those reactions together, they basically, because they're on opposite sides of the arrow, the equation there, basically, when you bring them to the other side, they essentially will cancel out. It's almost like math, right? You can kind of think of like the arrows like an equal sign. So basically you have on one side like N2O2 basically equals N2O2. So if you brought it over here, right, technically be like subtracting it, right? And it would actually cancel out, I guess, yeah. Other questions? Okay, so the first part of whether or not the mechanism is good or not is good here. So we did get that. Clearly, as I mentioned before, if you did that and it didn't add up to the reaction you're looking at, then it's not, you could just stop right there. It's not a good mechanism at that point. So the next thing we want to determine is we know that the rate law that was found experimentally should have the same rate law as the RDS or the slowest step in the mechanism. So here we have to determine which one is the slowest step or the RDS in this mechanism. And if you had to take a wild guess, which one would it be? I'm going to go with the one labeled slow. Yeah, so that seems like it's probably the slowest step in the mechanism. So sometimes in mechanisms, they will do that at the end of each of these steps. They'll go fast, fast, and slow. So that's a quite easy way to determine this is our RDS. So this is our rate determining step for this mechanism. This is going to be the slow step in the mechanism here. So if we write a rate law, and we could do that for each of these steps, but we're interested really in our rate determining step. This would be the rate is equal to K, H2, and N2O2, right? Now, I probably shouldn't take all those crosses off, but I'm going to recross off everything I did when I added the equation together. And in this reaction here, there are some intermediates, yes? And what are the intermediates here? They are the ones that I basically crossed out that are not found in the overall reaction, right? So we don't see N2O2 in the overall reaction. We don't see N2O in the overall reaction. So these are our two intermediates in this reaction, right? So what we want to do now is compare the rate law that we have here to the rate law that was found experimentally and see if they match. Do they match? The answer is you don't know yet, because even though they look like they don't match, the problem is we're not comparing sort of apples to apples, because in the rate law that we have for the slow step, we have this intermediate, right, which is not part of the overall reaction. That means that in order to truly compare the rate law for the slow step, we actually have to get rid of this intermediate out of that rate law and substitute in something that's kind of there in the overall reaction. So we have to kind of get rid of the intermediate so that we can truly compare the two rate laws once that intermediate's out of there. Now, to do that, we're going to use the other steps in the mechanism. And for example, we would look and perhaps find another step in the mechanism where there is N2O2. And that is like, for example, the first step here. That first step also is a reversible reaction. It is heading basically in both directions, right? And a reversible reaction, as we will talk about in the next chapter, will eventually reach equilibrium, right? And the rate of the forward reaction will equal the rate of the reverse reaction. So in this first step, we could actually write not one, but we could actually write two rate laws for that first step. One for what is referred to as the forward direction, going from reactants to products. And because it's a reversible reaction, some of those products will head back the other way and make reactants. And we could write a rate law for the reverse reaction, which would be going from products back to reactants. And in the case of the reverse reaction, our products would be like our reactants, right? And our reactants would be like our products as it's heading in the opposite direction. So if we write two rate laws, one for the forward one here for the first step, the rate of the forward direction would equal K1, which is the rate constant up here, times the concentration of NO and its squared. We could also write a rate law, as I mentioned, for the reverse direction, which again is heading in this direction, and it would equal K to the minus 1 N2O2. Now, one of the things we'll talk about in the next chapter, which is really what equilibrium means, is when this reaches equilibrium, the rate of the forward direction and the rate of the reverse direction will actually equal each other. They're going basically at the same rate, which means although I don't know what that number actually is, these two numbers are the same numbers. Yeah, they're the same values basically. And because they're the same values, we could actually set what's on the right-hand side equal to each other. So we could set, if we wanted to, K1 NO squared is equal to K to the minus 1 N2O2. Now remember, the goal here, right, is to find a way to substitute out our intermediate in this rate law, right? So what we want to do in this case is we actually want to solve for this, yeah, because that is what we want to get rid of in our rate law that we wrote for the second step. So very simply, all we have to do is divide that to the other side, right? And that will give us that the concentration of N2O2 equals K1 NO squared divided by K to the minus 1. First off, any questions on that? So the goal here is to get rid of that intermediate in our rate law in the second step. We're using the first step in the mechanism basically to solve for the intermediate to figure out what it equals. And now what we're going to do is, now that we know that the concentration of N2O2 equals this guy, we're going to actually substitute it right into there, yeah, where it was in our original rate law for our second step. So if we do that, I'll just do a big, maybe not do into there, yeah. All right, so if we do that and we substitute that into the original rate law that we wrote for the second step, step 2, we take the rate is equal to K, my H2 And now substituting that in there, I'll do everything that's written, NO squared, oops, divided by K to the -1, right? Now, I also see something else here in the what I just did, which is this is a rate constant, right? That's a rate constant, and frankly, that's a rate constant. And since it's a rate constant, are they all the same or different numbers? Same, right? So what is going to happen if we reduce this down a little bit more? Any one of these K's you want to take out, those guys are going to basically cancel each other out. And that's going to leave us now that the rate is equal to K H2 NO squared. Yeah. Now we have something that does not have an intermediate in it, and we can compare it to the observed one. Does it match now? It does match now, yeah. And it is going to be actually a good mechanism, yeah. A plausible mechanism, really, if you want to call it that, which is what most people would call it. But again, here, so this is another type of mechanism problem where they sort of give you the mechanism and they ask you, is it a good or bad mechanism, essentially a plausible mechanism, and you have to kind of prove it. And in a situation like this, where your rate determining step has an intermediate in it, you have to get rid of that intermediate by using the other steps, basically, so that when you get the rate law without the intermediate, you then have something obviously to compare to. Clearly, at this point, if we put everything into that at the end and it did not match, at that point, it would still be a bad mechanism, right? But in this case, it did match, so it is a good mechanism. Questions on that there? Yeah. You could you technically use any of them. I would say in a lot of cases, if you have a problem like this type of mechanism problem, probably the one that's like a reversible reaction is usually the one that you're going to go to, because that's going to be the reaction is going to give you something that you can kind of set something equal to something and then solve for it. But technically speaking, you could use any of the other steps. But I was saying in a lot of cases, it would probably be that step that is that. And it may be the first step, it may be the second step, maybe any of the steps along the way. Yeah. It's just the way they, that's just the way they kind of use it for the labeling it. So they could have used, for example, K1, K2, K3 along the way, but they use K -1 because in the forward direction is K to the 1. So they figure K to the -1 is like the reverse direction. It's just the way they kind of numbered it. And like I said, sometimes they'll number it like that. A lot of times they will, but in some cases they may just go like, K1 going the forward one, K2 going the back way and stuff like that. Yeah. It is. It's like a subscript, yeah. So it's like K to like the -1. Yeah, kind of like the K to the 1 is a subscript. Yeah. 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 So in most cases, you're probably going to only do it with the reversible reaction because in most cases, you're going to need to probably substitute out something. And if you don't have a reversible reaction, you kind of just have like, that's just what it's equal to kind of thing. So it's usually going to always be the reversible reaction. And again, like another question, the reversible reaction may not always be the first step. It may be maybe a different step, but that's always the one that's going to allow you to kind of get something that you could kind of substitute in there for it. Yeah. Say it one more time. Intermediates are things when you add the equations together, the things we canceled out that are completely canceled out and do not appear in the overall reaction. Yeah. So that's the key to it. So there may be times like we had, I think on the previous one that we did, for example, this one, when we added this together, this canceled out, right? And this canceled out. But we still had NO2, and that NO2 at the end was still in the overall reaction. So even though we sort of canceled out or kind of reduced NO2, because NO2, when you take this down, would still be in the overall reaction, is not considered an intermediate. So the definition of intermediate is something that's made early on in the mechanism, but gets completely used up by the time it's over. So it should never appear in the overall reaction. So in this case, the only intermediate in this one would actually be just the NO3 because it would not appear in the overall reaction because it got completely canceled out. So sometimes that does happen, like we had on this one, where you may not completely cancel something out, but kind of reduce it down. And if that thing still appears in the overall reaction, it's not considered an intermediate because it should not be in the overall reaction. Otherwise, it's not an intermediate. No. Okay. Other questions? Yeah. I'm sorry. Say it one more time. Where I substituted? Yeah, I substituted in originally when we first started. We wrote it's the stuff that is highlighted here, right here in green, right into here. This was the original rate law from step number 2. If you wrote the original rate law for this elementary step, it's K, H2, and N2O2. So this was the intermediate in that rate determining step that we need to get rid of. And this is where I just threw everything into that spot right there, if that's what you're asking. Yeah. And when I did that, it ended up basically being this on the bottom. Yeah. Other questions? Yeah. Yeah. So remember, this is the only place in kinetics where you can actually use the coefficients from the equations as the orders, and that's where that came from. Uh, and again, we don't do that early on. With all the other stuff we did in kinetics, we don't use the coefficients. But when you're doing elementary steps in these reaction mechanisms, it's permissible, and you can use the coefficients as the exponents. Yeah. Good questions. All right. Well, why don't you try one since I tried one? Why don't you try this one? So the reaction here mechanism, I think the 2 goes down here. I'll throw it down there. For this one is 203 goes to 302. The mechanism or the rate law is observed to be K is O3 squared and O2 to the -1. Based on this mechanism, is this a good or bad mechanism? So again, work through it and see what you come up with. Okay, so let's take a look and see. So remember, in this type of problem, basically there's 2 things you're gonna need to make sure of to really determine if this is sort of a good mechanism, bad mechanism. First thing is pretty simple. We just need to add up all of our steps. And again, it should come to the overall reaction if it is good. So we'll do that first here. We're gonna be looking for anything we could reduce down or cancel out completely. And it looks like in this case, the O there gets canceled out. And I think that is it. So that will leave us 203 on the left, and on the right-hand side, everybody stays on the right-hand side, we'll have 302. So that part of it checks out. In this particular case, our intermediate is going to be our O in this case, right? All right, so now that we have that, right, we then need to make sure that if this is going to be a good one, that the rate law that was found experimentally or observed matches the one for the rate determining step. And again, in this case, pretty easy to determine which one's the rate determining step. Again, the one that is labeled basically the slow step. So we do want to write a rate law here for our slow step, and that is the rate is equal to KO3 times O. Once again, at this point, we cannot compare, even though if you did, you might say it does not match, right? Because it doesn't look the same. We do have, once again, that intermediate in our rate law that, in a sense, we do need to kind of get rid of here so that we can kind of compare, again, that sort of apples to apples. So in this case, we actually only have one other step that is sort of useful here to kind of do that. And we're going to go to the first step here. And again, it is a reversible reaction, which means it's going in the forward direction and the reverse direction here. And in this, whoop, come here. There we go. Something to write with would be good. In the forward direction and in the reverse direction. So again, we have the ability to basically write 2 rate laws for that. So going in the forward direction here for step 1, the rate in the forward direction would equal K times O3. Now going in the reverse direction, again, our products become our reactants. So the rate of the reverse direction would be O2 and O. Once again, these 2 rates are going to really be the same as this reaction is going to reach equilibrium. And sometimes they may even write next to it fast, comma, equilibrium, basically to tell you that it will reach equilibrium. So again, we could set these guys equal to each other. So if we do that, that's going to give us KO3 is equal to O2 and O. Again, remember that we really want to get rid of the O here and kind of substitute out for it. So in this case, we're going to divide this to the other side. that will give us that the concentration of O is equal to, I feel like I lost a K there along the way there, so there should be a K to the -1 there, K to the -1. So that's going to equal, pop it back in here, maybe K O3 divided by K to the -1 O2 here, yeah. So, so again, I'll put it here, K to the -1 there, and put it better here, K to the -1. All right, so we're going to now have something here. We're going to take this entire thing because that does equal the O, and we're basically going to pop it into our original rate law there, and that will give us the rate is equal to K O3, and just basically writing it to like it was, K to the 1, O3 divided by K to the -1, O2, right? Once again, we could do a little bit of reducing here and kind of cleaning up here to make it look a little better. Again, two of these are going to cancel. That's O3 and O3, which is O3 squared, right? So that's basically K O3 squared divided by O2 is our rate law. Now we have something that we could compare. So we're going to compare our rate law here to our rate law there. Do they match? They do match, yes. And again, this is O2 to the -1, which basically means 1 over O2, right? And that would put the O2 on the bottom here, yeah. And so it does match. So again, this would be a good one as well. So I would say this type of mechanism is kind of like, math where you got to proof it. Yeah, kind of you got it and you got to prove that it is or not a good mechanism. Yeah. Can you cancel out the K's where now? I'm sorry. Hmm. You mean up here? Oh, sorry. Oh, here? Yeah, yeah, you can if you want. At some point, you can cancel it. I just put it in there so people don't uh, wonder where they went to along the way. But yeah, you can. At some point, you can cancel that out because it is the same. So it will eventually cancel out. Yeah. Other questions? All right. One last mechanism problem here. We want to determine the overall reaction, the rate determining step, and the rate law, and identify any intermediate. So why don't you give that a go on this one and see what you come up with. A little bit different type of mechanism problem. Take a look. So on this one, we want the overall reaction. So we're just going to simply add them together. Again, anything on opposite sides is the same, can cancel out or reduce down. So B is going to completely cancel out. And I think at that point, that's everything. So everybody on the left-hand side stays there. So 2A plus B to the 2 goes to 2AB would be our overall reaction in this case. We could see here that B was made in an earlier step and completely used up in a later step. So obviously B here would be our intermediate, right? And lastly here, the rate determining step should be the first step here, right? So that is the slow step in the mechanism. And because that is the slow step in the mechanism, we could write the rate law for that slow step, which is basically for step 1, which is our RDS. And that would be K times A and B to the 2. And that should be the rate law for this particular reaction, right? And clearly we're good when there's no intermediates or anything in there, obviously. And that should be all of that, I think. Any questions on any of that? So these are kind of three different types of mechanism problem. One, like we did first on kind of the middle one, and then this one where you could kind of deduce everything from a proposed mechanism that's there. Yeah. Any questions on any of that? So how do these mechanisms sort of relate, for example, to energy, right? For example, let's say we had a two-step mechanism, right, where we had A plus B goes to C plus D, and we'll just say this is, we'll go with the fast step, why not? And C plus D, right, goes to E plus F, and this is our slow step, right? So this would be our rate determining step in this mechanism. Obviously, if we added this together, as we saw earlier, A plus B goes to E plus F, as C would cancel and D would cancel, right? So if we were thinking about sort of energy diagrams like we saw earlier, right? Um, we could draw sort of an energy diagram, if you will. Progress, right? The reaction progress happening there. So we would start with our reactants, right? And those would be A plus B, right? And we know we would have, right, an activation energy hill that has to climb to get to the other side. So it would climb, right, and come down. And it would come down, right, to really our intermediates, right? And now at this case, we have our slow step, right? And this guy would then perhaps come up and go that way. We'll just make it like that. Why not? And it would go to our products in this case, right? Now, this is our first step, right? And this is the activation energy, really step one, right? And the activation energy here, right, would be for our second step. What is the difference here between the activation energies? Am I exaggerated just up there? Which one has the greater activation energy? Step two. And that makes sense because step two is slow step, right? So it's going to take longer to get up that hill, right? So obviously, if it was reversed, for example, like the first step was a slow step, if you were to draw something like this, the first step should have a bigger activation energy than the second step. Does that make sense? By the way, we also could determine this reaction would be exothermic or endothermic in this case. To determine that, if you're again not sure, like we talked about with the energy diagrams, we're basically looking at the energy of our reactants to our energy of our products. All right, delta H of the reaction, products minus reactants, right? So our products here are higher in energy, so larger number minus our smaller number gives us a positive value, right? Reactants are lower in energy than products, always means, right, endothermic, got to put energy in to do that, right? Obviously, if you're going to draw something like that, that's also something that you want to think about. Is it an exothermic reaction or an endothermic reaction, and the placement of like your reactants and your products, right? So if it was exothermic, my placement, my products should actually be right lower than where my reactants started, right? So those are some things you want to think about if you're asked to draw something like that, which you might be in a lab coming up. Yes, and some post-lab questions to draw some of these type of diagrams. So those are things you want to think about. If you have a slow step, should definitely have a bigger activation energy than the other steps, and also the placement of reactants and products in terms of their energy levels, as to whether or not the overall reactions exothermic or endothermic. Any questions on that there? All right, that should wrap up this chapter, I think. We're out of chapter, I think, here. Let's see. Yeah. Yes. Well, we talked a little, I guess not. We got a little bit, I guess. We talked a little bit about catalyst just to finish up. Again, a catalyst, as we talked about, we sort of talked about throughout the chapter, again, is a substance that typically will increase the rate of the reaction. And really, the way it's able to do that, as we talked about earlier on, is it's able to, again, find a more efficient energy pathway for that reaction to occur. And that allows a greater amount of reactants really to get to the other side. And ultimately, by finding that sort of more efficient pathway, what it's able to do is actually lower that activation energy. So it's able to lower that hill. And by having a much smaller hill to sort of climb to get to the other side, that again is going to kind of open up the product side to a lot more reactants to be able to get up and over. The end result of that is you're going to get a lot more reactants getting converted into products, and the rate of the reaction should increase. So our activation energy goes down, our rate constant will go up, which would increase the rate of a reaction. Remember, a catalyst is again not a reactant, it's not a product, it does not get used up in the reaction, it's there just to really facilitate the reaction occurring. Yeah, it probably a true definition of a catalyst is really something that's not either of those things. So for example, like the experiment we're doing are currently doing. The HCl technically is a catalyst, but we are treating it more like a reactant. So, and we are putting it, even though it doesn't technically appear in the overall reaction, we are putting it into our rate law and stuff like that. So, in certain cases, sometimes people will do that and kind of treat it and as like a reactant, like if you're trying to figure out something like a rate law and its dependence on the reaction. But technically speaking, even that experiment we're doing, the HCl really is a catalyst. It's not really a reactant, but we're kind of looking in the context of the experiment to see how that catalyst is affecting the rate of the reaction. Other questions? All right, so obviously the rate of the uncatalyzed reaction would be greater than the uncatalyzed reaction, and again, we will see a lowering of the activation energy. Now, there's different types of catalysts, and again, they may be a heterogeneous catalyst, which means that the catalyst and sort of the reactants are in different phases, like a heterogeneous mixture. You can see different phases and stuff like that. So maybe your catalyst is a solid and your reactants are gases, like the Haber process there for ammonia. The making of ammonia actually will occur, but it's a very slow reaction if you don't use a catalyst. To make nitric acid as well. In our catalytic converters, right, there's a couple of catalysts in those if you have a catalytic converter on your car. There's actually two different types of catalysts that it goes through, which is it has precious metals in there that act as the catalyst, which is why people chop them off your car, right, and take them out for that, what's inside there. My favorite email ever from Mousak was, if you see somebody walking through the parking lot with a circular saw, you should probably report it. I'm like, all right. They're like taking people's catalytic converters off their cars. I'm like, that's quite an email. Um, in a homogeneous, that was a long time ago, so I'm sure your car is fine out there right now. In a homogeneous catalyst, acid catalyst or base catalyst, sometimes again you'll see that written like in our experiment. Really, H plus means an acid catalyst. And again, usually that everybody's in the same phase, like in the experiment we're doing, right? Everybody's basically solutions, right? So even our HCl or acid acting really as a catalyst is in the same phase as everybody else. And that's sometimes needed really just to provide a proper sort of environment in terms of pH to allow everything to occur a lot more efficiently. Here's the example, for example, the Haber process. Without the solid catalyst being there, these gas molecules got to fly around and hope to come in contact with each other. As we talked about, with that catalyst being there, it just sort of directs everybody to a centralized location. And the catalyst also kind of helps in kind of rearranging the molecules into ammonia and allows for the reaction to occur a lot faster. Nitric acid being made as well uses a platinum as a catalyst. And again, you can make some nitric acid. One of the nice things about nitric acid is some of the products you make in these reactions are actually some of the reactants that you need. So it can make a lot more sort of the nitric acid as you go through it. There is our catalytic converter in our car, which is used to treat and not have pollutants go out in terms of hydrocarbons from your tailpipe. And again, hopefully no chop chop and off it goes, right? And that kind of stuff, right? All right. That should wrap up, I think, the chapter here. All right, that is chapter 12. We're going to go off to chapter 13 now, if I can find it. Let's hope so, maybe. So, there it is. We'll go that one. Okay, we're going to go to chapter 13, which, dare I say, is the start of real Chem 51 here. It's all about equilibrium. So this is our chemical equilibrium chapter, and we're going to talk about, as I mentioned earlier, every type of equilibrium you never want to know about. And this part of the class is brought to you by the letter K. We're going to talk about all kinds of K values, every type of K value you like. And the first thing we should talk about is sort of what we were just kind of saw in some of those mechanisms. When we talk about chemical equilibrium, it is a certain type of reaction that's involved in that, and those are reversible reactions. And these are the type of reactions that are involved in equilibrium. That is something where you see those arrows heading in both directions. And as we talked about a second ago, when we're doing some of those mechanisms, there's basically two directions that we talked about. So again, if you're going from reactants to products, that again is what is referred to as the forward direction. And what will happen at some point when this reaction occurs is you will build up enough products that the products will decide we would like to react with each other and actually go back the other way. And that is going to kick off, again, what is referred to as the reverse direction in this reaction. Now, people oftentimes have a misconception about the word when something reaches chemical equilibrium. And when people think about things reaching chemical equilibrium, what they oftentimes think about is, oh, that must mean that we're like equal things on both sides. And because it says equilibrium, so people think equal. And that's really not what equilibrium means or refers to. What it refers to is actually what we were talking about in the previous chapter. It refers to the rate of the forward direction will eventually equal the rate of the reverse direction. So that is what it means when it reaches chemical equilibrium. It's that rate of the forward direction will eventually equal the rate of the reverse direction. So what does that do to a reaction that's happening here? What that does to a reaction is once it reaches equilibrium, if you're talking about concentrations, the concentrations of your reactants and your concentration of your products essentially get locked into place of where they're at. So, and they will not change. So, if we started with, for example, here initially 4 molar of this guy and maybe 6 molar of this guy and nothing on this side. And then it reaches equilibrium, right? And we'll just say we had 2 molar of this guy, maybe 3 molar of this guy, 2 molar of this guy, and maybe 4 molar of this guy. When it reaches equilibrium, these concentrations here and these concentrations here will stay the same and they will really not change. And that's because the rate of the forward and reverse direction are equal to each other. So just as quick as you make some products, it's just going to shoot back the other way, right? And that's just going to essentially just lock everybody into place in terms of their concentrations. If we're dealing with pressures, which we sometimes do with equilibrium, it will also lock everybody in place with their pressures because you essentially have the same concentration of those gases, and that will lock the pressures basically into place. They will essentially remain that way unless you do something to screw up the equilibrium, which you can. And you can screw up the equilibrium. But the nice thing about this, as we will talk about, is even if you try to screw up the equilibrium, you may succeed, but it will find a way to get itself back to that equilibrium state. So these type of reactions are pretty interesting in that sense that you could actually mess it up, but then it itself will self-correct itself to get it back to a state of the forward direction, the reverse direction will equal each other and back to equilibrium. And you could actually force it to go one way, and then you can actually force it to go back the other way. And again, it has a lot of kind of self-correcting in these type of reactions. So when we talk about equilibrium, as I mentioned, one of the things that's also hard for people to sort of understand is on the molecular level, there is a lot of activity happening. But when you look at like your beaker, image may look like it's over, right? So you may do a reaction that maybe produces, as I have read, a red solution, right? At equilibrium. And when you look at your beaker, it just looks like, hey, it's been red for an hour, right? Nothing much is happening in there, right? But because this is a reversible reaction, we'll just say that was this reaction. There is a lot of activity happening to keep it red. There's a lot of A plus B going over to C plus D and a lot of C plus D heading backwards to basically maintain where it's at. So even though it may appear to you when you look at kind of the big picture, the beaker, whatever it may be, that the reaction is over, there's a lot of activity happening back and forth constantly to basically maintain where you're at. And that's different than sort of a one-way street arrow where everybody just dumps out to the products, it's over, nobody's coming back really the other way. When you have this one arrow heading to products, it's just like a one-way street kind of thing, as opposed to like a two-way street where you can kind of go in both directions. So equilibrium, as they say, is static microscopically, but very dynamic microscopically or macroscopically is static. So how do you know if you kind of graphically looking at, obviously this is our ammonia formation, which is a reversible reaction here. maybe a 2 there, like I'm in chemistry class here, maybe a 3 to balance it. And initially, when this reaction starts, for example, we may only have, as we can see from the graph present, we only have reactants present, right? And we basically have no products present at the beginning of this reaction. So because we only have reactants present, there's only one choice really for this reaction to occur. It could only occur in the forward direction, right? Because you have no products that could go backwards at this point. So at this point, when this reaction starts, the only thing that's possible is the forward direction in this reaction heading towards products. And we see that in this as the concentration of our reactants start to decrease. And as that forward direction occurs, we now start to see some products being made, right? So we start to see some increase in our product formation. At some point, as this forward reaction is occurring, you will generate enough products that they will decide, hey, I like to go back now the other way. And you will start to have the reverse reaction occurring, right? And what you can maybe see is at some point, the decrease in our reactants starts to almost level off a little bit. It's not as steep, right, of a decrease. And that's where we're starting to get a lot more perhaps of our reactants, our products going in the other direction. And its increase also starts to kind of slow down a little bit, right? It's not just going linearly up, right? It's starting to, we're making some products, but not as much as we were. And that's because at this point, we now have everybody heading in both directions, right? We got the forward direction, we got the reverse direction basically happening. And at some point, they're going to lock into equilibrium. And we can see that when we talked about it, which is when everybody's concentration basically gets locked into place. And that in a graph is shown where everybody's concentration levels out, right? When you have a straight line on a graph like this, that means that your concentration is no longer changing, right? It's basically locked into place. And that is the point here where it basically flatlines everybody, that chemical equilibrium has been reached. That's the point where the rate of that forward direction will equal the rate of the reverse direction. Any questions on that there? Yeah. Um, the answer is no, in a sense. So we'll talk about there's only certain phases that have an effect on the equilibrium and really sort of participate in the equilibrium. Most of the time, what phases sort of participate in the equilibrium are things that are in the gas phase. So you think about they're flying around and moving, and things in the aqueous stage, which has basically ions and stuff floating around in the solution. So those are really these phases that participate in the equilibrium. So you can have, for example, an equilibrium reaction where you do have different phases involved, but not all of those things may actually participate in the equilibrium reaction per se. So you could have one where you have a solid that may not participate. You could also have one where you have, like, for example, like a pure liquid, and pure liquids have usually a fairly high concentration that don't really change all that much over the whole reaction. Like, for example, if you have water in the liquid state, its concentration is high enough that it really doesn't change all that much through the reaction. So even though it's sort of in the equation in terms of the equilibrium part of the reaction, it's really not participating in it. So you can have, you could definitely have different phases in a reaction, and maybe not all of those things would participate in the equilibrium. Other questions? So for example here, initially in this reaction here, we have no H2 and CO2 present. So as I mentioned before, in this case, if you're really starting with all reactants, the only option for this reaction is to kick off that forward direction. And as we sort of saw in that graph, eventually you'll kind of build up enough of these guys that you'll start seeing that reverse reaction really starting to increase. And again, it will continue this process as we talked about until it reaches chemical equilibrium, which again is that rate of the forward direction equals the rate of the reverse direction. And as I mentioned before, graphically speaking, you should see sort of the forward reaction concentration rates start to decrease, the reverse one will start to increase as you start to make products. And again, they eventually will kind of level out with each other. All right, so when we think about this one, consider an equilibrium mixture in a closed container that contains H2O plus CO, makes some H2 and CO2. What would happen to the concentrations of everybody in this reaction if you decide to add more water to it? So take a moment and think about what would happen to this reaction if you decide to add more water. Would everybody's concentration stay the same? Would some go up? Would some go down? So decide which ones would go up and down. So just think about it for a second and come up with what you think. In this case, and one of the things that sometimes people also have a hard time sort of visualizing, if we have a reaction that's at equilibrium, you let it sort of reach equilibrium. What that does mean is just so we're clear, if it's, aqueous or if it's gas like this, basically everybody is kind of in the pool together. Yeah. So everybody's in there. You got a little bit of everybody sort of around and moving around, in the solution. If it's a solution, if it's in this case, you got some gas molecules, everybody flying around and stuff like that. So everybody's in there and it has reached equilibrium at this point, right? And now we're going to add some more H2O, right? So when we add more H2O, which is over here, what should happen to the concentration of CO? Should it stay the same? Should it go up? Should it go down? What do you think? Well, let's start with when I add H2O to the left-hand side, I am adding more reactants or products? Reactants, which now means that I now have a lot more reactants available than I do products, right? So there's most likely going to be a greater chance that the reactant molecules are now going to be able to find each other, right? A lot quicker than perhaps the product molecules. And that should kick off this reaction heading in which direction? The forward direction or the reverse direction? Yeah, so since we have a lot more availability of reactants, that really should kick off the forward direction. And if it kicks off the forward direction, the only way to make products is my reactants need to go down, right? So we would expect the concentration of CO to start to decrease because we're now really forcing this reaction to go to the product side. And the only way to make products is you got to use those reactants to make the products, right? That would also mean that when I come to my product side, the concentration of H2 should start to increase, yeah. And the concentration of CO2 should also start to increase, again, because you are really pushing the forward reaction occurring in this case. Now, what about water? Water's concentration should actually go, in theory, it should go down, but what you would actually see is because you added it, you would see it probably jump up high because you just artificially added it. But eventually, once it starts reacting with the other reactant there, it should make its way back down, right? And in the case of water, it may actually end up higher than it started with, only because maybe you put it in, you obviously put more in there. But ultimately, it should also come back down as it starts reacting, and the forward direction should start to occur. Any questions on that there? So what would happen if we looked at the same reaction, but instead we added some more H2 in this case? What should happen to CO2's concentration here? Should it go up? Should it go down? Should it be the same? So let's walk through this the same way. If I add H2, I just added more reactants or products. So that's going to now make the products more available, right, than the reactants. And because the products are more available than the reactants, which reaction should occur? Forward direction or the reverse direction? The reverse direction. Again, because of the availability of products, it's not going to take them very long to find each other. And that really should kick off the reverse reaction in this case. And when it kicks off the reverse reaction in this case, and the only way for that to happen is basically our products are like our reactants, right? They have to be used to go back to the reactant side. So we should see a decrease in the CO2, we should see some increasing in the concentrations of H2O and CO, because again, the reverse reaction is happening. And in the case of H2, once again, we're going to kind of see the same effect. It's going to kind of go up, and then we'll start to come back down as it reacts with the CO2 in that reverse reaction. Any questions on that? So essentially what we're thinking about here is, are we doing something that's going to cause the forward direction to occur? Or are we doing something here that's going to cause kind of the reverse direction to occur? And that's going to have an effect, obviously, on the concentration of your reactions or products, depending on which direction that reaction is kind of predominating at that point in time. Any questions on that? By the way, this is, as I mentioned earlier, a way you could do with an equilibrium reaction to force it, for example, to go one way or the other. So if I wanted this reaction really just to only go to the left there towards the reactant side, I could just load up with a really high concentration of one of those products, and that's going to cause basically that reaction just to shoot over to the other side, right? You're kind of like forcing it to go that way. Or vice versa, I can load it up with some reactants, and it's going to force it for temporarily, right, to head to the other side and kind of force a lot more product formation. So you could kind of use the equilibrium sometimes to your advantage. We'll actually do that in an experiment coming up where we kind of, even though it's a equilibrium reaction, we kind of force the reaction to almost be like a one-way reaction and force it only to kind of go to the product side. Any questions on that there? Get that there. So let's talk a little bit about the equilibrium constant and its application. So if we have this reversible reaction, there is a relationship that is a constant relationship, and it is, as I mentioned before, the equilibrium constant. This is capital K, not lowercase k, as we know is the rate constant. So this is capital K, and that is the equilibrium constant. And as I mentioned earlier, it is the letter this class is brought to you by here. It is an equilibrium constant, which means it is a constant value for a reaction exactly the way it's written at a specific temperature. So as we will talk about, the one thing that can actually affect the value of the equilibrium constant is actually temperature. So if you change the temperature for a reaction, you will end up at that new temperature with a different equilibrium constant than you had at the old temperature. Now, the relationship of this is basically to calculate the equilibrium constant. You basically take the concentration of your products divided by the concentration of your reactants. And when you do this with concentration, this is sometimes referred to as the Kc value. I'm going to go with concentration for the C. It seems like it makes sense. So we'll go with Kc. That's what the C refers to. That's our first of 400 K values we're going to talk about as we go through these chapters. But Kc is the equilibrium concentration, or the equilibrium constant using concentrations. Now, one thing that we do here with the equilibrium constant that we don't do, obviously, with the orders and like the rate constants, is we actually do use the coefficients as the exponents. Obviously, that's a 1. So we do take the concentration of the products over the reactants. We do use the coefficients in the balance equation as the exponents for that. Now, the equilibrium constant is frankly just a number, no units associated with it. So it's one of those few things in chemistry that actually don't have units. It's actually just a number. And in general, if we have a reaction like we have here, we will take our products over our reactants, and you will get your concentration of C to the C, D to the D, divided by A to the A, and B to the B. The equilibrium constant, as I mentioned, is a constant value for that reaction. Now, since it's just a number, it does tell us a couple of things. So, for example, if I have a large value of K, what would that mean when I reach equilibrium? Would I mainly expect to have reactants or products present? I would mainly expect to have products because just mathematically speaking, if that's a large number on top divided by a small number, you get a large number, right? So if you end up with a large value of K, you can make a pretty good assumption that perhaps you have more products present than reactants. And vice versa, if we had a small amount or small value of K, we would expect it to have more reactants present for the same reason. In order to get a small value, your top number needs to be smaller than your bottom number right there. So if we have a larger bottom number there, we will end up with that. What is considered for an equilibrium constant, a large value versus a small value? One, that big number of one, is considered large. Yeah. So anything above one is considered a large value of K. Anything kind of less than one is considered a small value of K. And there is definitely extremes to that we will see. There are some K values that are like times 10 to the 34 power. And there's some K values that are like times 10 to the minus 52. Right? So there's way extremes everywhere in between in terms of equilibrium. Now, clearly, if you're at the extreme, like, K values times 10 to the 34, it is essentially, even though a reversible reaction, like a one-way street, right? It's all going to go to products pretty much. Or if you're at the minus 52 times 10 to minus 52 side, it's going to pretty much all be reactants. You're not getting much products formed. But even at those extremes, as we will learn, it is still a reversible reaction. So even though it is almost 100%, for example, in the extreme case, going to the product side, there will still be just a smidgen of it working its way back the other way, a very, very small amount, because it's always going to be a reversible reaction. Even if you try to force it all the way one way, you will still have some guys coming back the other way, even in those sort of extreme conditions. Now, the K value is the same no matter what you start with. And that also is something that people have a very hard time with when they talk about equilibrium. So what do I mean by that? I mean, for example, you will end up, if you did multiple experiments, for example, right? And let's just say we did these experiments at 25 degrees Celsius, and you did multiple experiments, experiment 1, experiment 2, experiment 3, experiment 4, however many experiments you want to do. And let's just say in experiment 1, we started with, all reactants and no products, right? Even if you started in experiment 2 with no reactants, all products, right? Yeah. Maybe in experiment 3, you had a little bit of everybody involved there, right? And so forth. So we'll just go 4. So that's right, more. So no matter what you do, if you start with all reactants, you start with all products, you throw a little bit of everybody into the pool together, right? They're all swimming together. You will end up with the exact same, or should end up with the exact same K value. Yeah. And sometimes people think, well, wait, I started with like more in this one and less in this one. I should end up with different K values. You will not. You will end up with the exact same K value because the temperature never changed. And that's the only thing that could affect it. Now, you may be saying, how can that happen, right? So let me just use a very simple explanation, right, of how that could happen. What is the equilibrium constant here? It is essentially a fraction, right? So it's products over reactants, right? It's a ratio of the amount of products you have to reactants. So if we think about math, right, and let's just say I wanted to end up with a K value of 2. There are many ratios that will give me 2. I could go 4 over 2 is 2, right? I could go 2 over 1 is 2. I could even do some advanced math here and go 8 over 4 is 2, right? Those are all different product reactants, right? But they all end up where? They all end up in the same ratio. And that's what happens with these reactions. So again, sometimes people think like I used way more reactants in this trial than I did in the first one. I should end up with a different K value. And you won't, because as long as the temperature stays the same, the ratio of what you will get in terms of your concentration of your products to your reactants will always be the same ratio. And that's what we talk about when it's an equilibrium constant. Now, what we're talking about when it changed temperature, it changes the K value. Let's say I did these exact same 3 experiments, but I did it at, 40 degrees Celsius. At 40 degrees Celsius, I would have the exact same experiment. And at 40 degrees Celsius, the K values that I would get for all three of those experiments, would they be the same at 40 degrees? They would be, because I kept it at 40 degrees for all three of those experiments. I should end up with the same, right? When I compare the K value at 40 degrees to 25 degrees, will those guys be the same? They will not be the same. So that's what we're talking about. When you change the temperature, the K value at one temperature versus the other will be different because you change the temperature. And because of that, the energy and stuff will allow a different proportion of products to reactants to occur, because you change kind of like a variable, if you will. You change the temperature. And as we know, right, the temperature can either kind of speed up or slow down a reaction, right? So that will get you a different ratio of products to reactions than you would get at a different temperature. Any questions on that there? So that's a really hard concept for a lot of people. People always think like it definitely use different amounts, I should get different K values. So again, that temperature is really the only thing that affects the value. And as long as you keep that temperature constant, you can do as many experiments you want with whatever you want to throw into the pool. That ratio of products to reactions should be the same. But as soon as you change the temperature, comparison of K value from temperature A to temperature B, you'll have K values. Yeah. Any questions on that?